Hey guys, let's take a look at this problem. The graphs of the polar curves are... Oh, this one you can use calculators. One calculator. Don't use... Why would you use more than... Okay. The graphs of the polar curves r equals 3. That's this one. That's that. That's a circle. And r equals 3 minus 2 sine 2 theta. That's this part. This probably looks like a little thing there. Are shown in the figure above for 0 to pi. Oh, it tells you. That's nice. From 0 to pi, that means this is pi over 2. Sweet. Sweet. A. Let R be the shaded region that is inside the graph of R equals 3 and inside the graph of the... so shaded. There it is. Find the area. So the first thing that I'm thinking about is like, well, what's the area formula? Well, you could just memorize it, or what I do is I think of like an area of a sector, because this comes from areas of sectors. So, because like you're getting areas of sectors, all like an infinite number of sectors when you go and get this area. So the way I think about it is, if I have a cycle and a sector, I'm going to call this d theta. That's my angle there. It's an infinitely small angle if I'm using the integral. And I have pi r squared for this. That's the entire circle. But I don't want the entire circle. I want only part of it. So I'm going to say d theta, which is this angle. How much of that from the whole entire circle? That's 2 pi is the whole entire circle. And then I cancel stuff out. Nope, not the 2. So there's a pi. So I really just have like 1/2 r squared d theta. So the area formula is 1/2 the integral from alpha to beta of r of theta squared. So I'm going to square it, d theta. So that's how I remember that formula. I actually don't remember it, but I remember how to get it. So it says find the area, and we're allowed to use a calculator. So I'm going to set up an integral and add some stuff, and then you can do it in a calculator. So this part, I know this right here is 1/4 of the area of the circle, and this circle has radius 3. So I'm starting out with that. So I'm having, for part A, I'm going to have pi r squared, so pi times 3 squared, okay, and then divide that by 4, because it's only 1/4 of it. And then I'm going to add the rest of it, this part, and then this is going to be using the integral from, well, 1/2 times the integral from 0 to pi over 2. We already decided that that was pi over 2. And I have my radius function, which is that. Oh, sweet. So then I have 3 minus 2 sine 2 theta. And I must square it. I must do that. D theta. So that will give me the area, and I can type all of that into my calculator. I can evaluate that. Don't forget to divide by 1/2. And there you go. That's part A. Part A. And if you round, you get 9.708. And there you go. That one is fairly straightforward, I think. Part B. For the curve. So maybe I should erase this. Okay. For the curve, r equals the... Okay, so it's this curve. Find the value of dx d theta at theta equals 6. You could also do this in the calculator. You just need to know what x is. Well, remember, take a look in your brain box and remember that x is equal, for polar curves, x is equal to r cosine theta, and y is equal to r sine theta. But it's only asking for dx d theta. So my x is just this, and r, because it says for this curve, r, there is a 3 minus 2 sine 2 theta times cosine theta. and you can actually put this into your calculator and take the derivative and plug in the 6. It allows you to do that. So the derivative, or you could just do it by hand using the product rule. First d second plus second d first, and then plug in pi over 6. No need to do that and waste time, though, because you have a calculator on this, and if in class you don't know how to do it, then you should ask me. So then, yeah, you can just take the derivative. It's with respect to theta, so you're really just straight up taking the derivative of that and plugging in pi over 6. So I cleaned it up a little bit. Let me erase that. So we have x. That's the x, and we plug in the a, and then you take the derivative of that. You can actually treat this as a y when you plug it into your calculator. This could be x, and then plug in pi over 6. That's all you're doing. And then take the derivative of that. So if you need help using the calculator, let me know in class. You can't let me know right now because it's a video. So that's great. A and B. Done. Easy. Easy peasy lemon squeezy. Why you squeeze the lemons? Because you're making lemonade. Okay. The distance between the two curves changes for 0 to pi over 2. Now, here's the confusing part, because it just says the distance, and they could mean, they don't. They mean one of these things, but it could be like the horizontal distance, or it could be the vertical distance between these two curves. But it's actually talking about the distance that also, like if you were to extend the line through these curves, it would always go through the origin. So they're talking about the distance from, like, let me draw it out, there to there, or like there to there. If you extended it, it would always go through. So there to there, there to there, there to there. So they're talking about these distances. So it's changing as theta changes. Okay, so that's great. Find the rate at which the distance between the two curves is changing. So really, I'm thinking, well, it would be nice if I had a function for the distance. Like if I had an expression that tells me the distance between the two, depending on some theta value. How could I possibly get that? Because if I had that function, then I could take the derivative, and that would tell me the rate. And then plug in that, because it says find the rate with respect to theta when theta equals pi over 3. So how the heck will I get this distance? Well, I just do the bigger curve, which is 3, r equals 3, minus the smaller curve. Why do I do that? Well, to find distance, I just have like the bigger... Actually, I have a formula that gives me that distance, that complete distance. And that is 3. It's 3 all the time. Okay, great. So that's what that distance is. And then I have a formula for this distance, and that also changes. And that one is given by this function. So if I want to find the distance from here to here, I just subtract this from that. Easy. So this function from there to there, that's going to be, maybe I shouldn't do it up there, but that's going to be r, well, I won't say r, but that's going to be 3, because that's the outer function, minus 3 minus 2 sine 2 theta. My stomach, did you hear my stomach? Maybe not. And then I'm just talking, that's weird. So I have that function, and then find the rate at which the distance between the two is changing. So this, again, you can use a calculator. But I'm going to distribute first. So there and there. So this cancels out, right? I get a negative 3 and a plus 2 sine 2 theta. So I have that. Great. Everything's working out. And so that's going to be my distance. And what I want to do is take the derivative of this and plug in pi over 3. And I could take it manually. I could take the derivative manually. So I'm going to say, I'm going to call this, let's call it d. So d theta is going to be 2 cosine 2 theta, and then I have to take the derivative of the inside times 2. I don't even need to do this. You could do this in your calculator. And then now I would evaluate it at d theta evaluated at theta equals, what was it, pi over 3. And then I can write that down, because that's what's, yes, pi over 3. So I just do that and I put it in the calculator. That one comes out to be -2. Or you could just plug it in. Everything, hopefully this is like, oh, easy, easy, easy. Because you can use a calculator, and it's like, I don't even know why. Well, I mean, I guess this one would take a little bit of time to evaluate. But you can still do it. You can still do it by hand. Now let's look at part D. Maybe we get some challenge here. Part D. So it says a particle is moving along the curve r equals 3 minus 2 blah blah blah, so that d theta dt is equal to 3. This is actually a related rates problem. Oh, perfect. And an implicit differentiation problem, because that's what happens in related rates. So, particles moving along the line, great. So that d theta dt equals 3. Okay, I don't know what's going on. That's fine for all times t greater than or equal to 0. And then it says, find the value of dr dt. What? At theta equals pi over 6. Now, you might read that and you go like, great, what does that mean? I don't know. What am I doing? I don't know. But it says find dr dt. I think I can do that. Except for there is no t here. There is no t. So, what does that mean? Well, let's just pretend like I'm just looking at a problem and I'm going to just scrounge up some stuff. Like I'm going to use as much as I do know. So if I'm trying to find dr dt, I'm taking the derivative of this with respect to t, even though there are no t's in this. Okay, so the derivative of a constant is still 0. Now I need to take the derivative of -2 sine 2 theta. Well, the derivative of the outside would be the derivative of the -2 sine. So that would be -2 cosine. You leave the inside the same. So cosine 2 theta. Everything's fine. Derivative of the outside with the inside the same, times the derivative of the inside. Now, here's where it gets interesting. I'm taking the derivative with respect to t of 2 theta. Remember, this t and that theta do not agree. So I have to use implicit differentiation. I just take the derivative like normal, which is 2, and then tack on a d theta dt. What? Crazy! And then, so that's dr dt. And I know that this is true because when I take the derivative and these don't agree, I have to use implicit differentiation. So, there we have that. And then now it says find when theta equals pi over 6. But we got a d theta dt. It also says that that is 3. So this part, oh, it's so easy. That's 3. This is pi over 6. Plug it in, bada bing, bada boom, and you get -6. So dr dt when theta equals pi over 6. Did I say -6? Yes. Very good. Find the value of dr dt. Okay. Easy. Man, this one, hopefully, you could get a 9 on this. I like that one. That was easy, in my opinion. You just gotta remember some things.